Okay, so we have so far discussed about discrete random variable as well as continuous random variable. So in the last class probably we have started discussing already about the continuous random variable and its associated PDF and CDF. So some of the property that we have already mentioned is something like this. One is, which is a universal theory of probability, that if Pxx is the PDF of a random variable x, and this must be 1, and then CDF and PDF are related like this. And of course its probability, so this must be greater than or equal to 0. So these three things we have already discussed about them. We have also told what do we mean by this PDF. It's a density function. Remember, even it is called PDF, it's probability density function, not distribution. So basically this Pxx doesn't give you probability, its value is always, or value at a particular x is always 0. It just provides the density, and that's why that other formula, that P, suppose x, not that equality, so that always comes out to be, this is always true. So from a particular value to another value, if we wish to calculate that our experiment, that random variable will lie between these two values, that has a probability term, and that probability term we get through integration of this PDF. So because it's a density function, so if you do integration, then you get the probability, but individual at a particular x you don't get anything. Okay, so we have also given an example of these things, right? So what we'll be doing now in communication, one of the most important PDF or most well known PDF that is being applied, we just give some property of that. It's just a quizzical thing. We need to just understand some of the properties and some of the functions associated with that. So that is called the Gaussian random variable, which is defined as this, defined by the PDF. That's one definition, or it can be, there is another definition where you have this. Right. So of course, as you can see, if I just put sigma equals to 1 and m equals to 0, I get back this one. Okay, so that's more generalized Gaussian distribution, where this m is called the, if you see, that's called the mean. We'll see how mean can be calculated for a random variable. So then we'll understand what do we mean by mean, and this sigma is means the standard deviation, or sigma square is the variance. Okay, so as long as the variance is 1 and your mean is 0, we get back to this, that definition. So this is a typical Gaussian distribution. If the mean is 0, it looks like this, the famous bell curve, or if the mean is m, so it will be centered around m, and it will look like this. As you increase the sigma, what will happen? This will become more and more flatter, and the top will come down. Okay, because the area under this must be always 1, and as you decrease the sigma, the top will go up and up, and this will become more sharper. Okay, so that's a typical Gaussian distribution. So what we'll try to see, this Gaussian distribution has been related to some other function, like they call it error complementary function, or error function, or the Q function. So we'll see what are those functions and how it is related. So that's something we'll try to define, because most of the times maybe not much in analog communication, but when you will be going into digital communication, you will see that this Q function, error function, those are the main functions which keeps coming back for your noise analysis or communication analysis with noise. Okay, so let us try to define a function called qy. This is by definition this given as 1 by 2 pi sum y to infinity e to the power minus x square by 2 dx. Now, this can be easily related to our that PDF or CDF as such. So, if Gaussian distribution we have already written as this Pxx is 1 by root 2 pi e to the power minus x square by 2. So, of course, the fxx will become minus infinity to x and then same thing, right. So, this thing with a dummy variable, let us say 1 by root 2 pi e to the power, or if we just put it with a variable y. So, this will become this e to the power minus x square by 2 dx. So, immediately we can see that this and this are complementary. Okay. So, I can write f x x equals to 1 minus q x. So, this is always true. Remember, it is a distribution. So, the integration of that from minus infinity to plus infinity must be 1. So, that is what we have applied over here, that minus infinity to plus infinity is 1 minus infinity to y. If I just take that out, this will automatically become y to infinity, right. So, that is the way they are related. There is another function which is error function or ERFC, that is defined as this 2 by root pi. So, these are just by definition, these functions are defined. So, this is called error complementary function. Okay. So, that is by definition is this this error complementary function, it is a function of x, of course. So, the integration, it is 2 by root pi. Okay. So, it goes from x to infinity e to the power minus y square. Immediately you can see what I need is to define it with respect to the Gaussian or q function. So, if I just go back to the q function, this has a relationship with the q function, but this is x square by 2. So, I have to replace it, y must be replaced as x by root 2, right. So, if I just do that, immediately I will be getting that particular function, and correspondingly what will happen, this will become 2q. Okay. So, just by doing that replacement and then changing the integration. So, y, if you replace it with respect to another dummy variable, take u. So, put it as u by 2, u by root 2, then immediately this will be u square by 2, and here that root 2 will be coming into the limit, and then you will see this will become just x root 2, and there will be a 2 factor which will be cancelled out. Okay. So, this is how it is, and you can also write. So, this q x can be as well as written as half just the reverse thing. Okay. So, here error f c or ERFC was written as a function of q x, and we are just doing the reverse thing, same thing, just a manipulation of should I put in the this one x by root 2 or x root 2. Okay. So, if you just put that, automatically you can manipulate and you can get this relationship. Okay. This is just to know that how this error function or error complementary function or complementary error function or this q function, how they are related to the Gaussian PDF. Okay. Because most of the time you will see that these functions are means numerically evaluated for different values of x. So, therefore, Gaussian can be immediately mapped to these functions. Okay. So, that is why it is often required. So, it is good to know these things. Okay. So, this was just for general information, so that whenever you are handling Gaussian function, probably you know these things. Okay. Now, what we will be doing, what we have already done for the discrete random variable, that joint distribution, conditional distribution, conditional probability, all those things, how do you define and characterize them in the continuous version. So, that is something we will start. So, first we will start with the joint distribution. Okay. So, that means we have two random variable which takes continuous value, one is x and another one is y. Okay. So, what I need to know is this, which is by definition written as probability that my random variable x is less than equal to some x, this x specified x, and my random variable y is less than equal to that specified y. Okay. So, this is called the joint CDF. Okay. So, whenever we talk about joint CDF, that means it is actually means there are underlying two random variable, and whenever we specify that joint CDF with two functional input as x and y, then we are actually saying that my it is the probability that one of the variable x, capital X, that is less than, always less than equal to some x specified over here, and the other variable capital Y is less than equal to this particular y. Okay. So, whenever this is happening, if we just calculate the overall probability that with what probability this particular thing phenomena is occurring, then we get this one. Okay. And with the same definition we can define because it is joint. So, there should be a double differentiation with respect to CDF to get the PDF, right. So, P x y with the similar mathematical thing which we have already proven, CDF and PDF are related to differentiation and integration. So, we can just write it as double derivative with respect to x and y. So, this is the corresponding density, joint density function. So, this is actually the joint density function that we were talking about. Okay. So, this actually tells you what it tells, I will list that. So, this like the single variable one, it P x y, its density. So, I have to multiply with the corresponding delta, means change of random variable. So, this defines a probability that my x or the random variable x is greater than x and less than equal to x plus del x. So, it lies between x and x plus del x, and the other one jointly both things are happening. So, the other random variable y, that is lying between y and y plus del y. So, that is the definition of the PDF, right. So, PDF is a density function as long as we multiply by the change. Okay. So, we get the area under that, and our assumption is this del x and del y are sufficiently small, so that things are not changing over there. Okay. So, this actually characterizes the probability that x lies at the vicinity of x, that means x plus x to x plus del x, and y lies at the vicinity of y, that means y plus y to y plus del y, right. So, this is the definition which we have seen already for single variable, right. It is just the extension. So, immediately we also know, because this is a probability. So, if we just integrate over all possible values of x and y, I must be getting 1, because that is a certain event, because I am searching through all values of x, all values of y. So, I will be getting something definitely. So, if I just integrate it from minus infinity to plus infinity, this p x y dx dy, that must be giving me 1. So, this is something again the fundamental postulate of probability theory, because it is probability. So, if I just integrate it over the whole region of interest, I must be getting 1. Okay. So, this will be always happening. Let us try to see the from joint distribution in our other case, the discrete random variable, we have defined the marginal distribution. Let us try to see whether that is happening over here. So, same definition, similar definition of marginal distribution. So, let us try to characterize this thing, that this is my marginal distribution. Okay. So, that means now I have made it free of y. I knew that there was a experiment which was going on where two variables were randomly varying x and y. So, but I am interested in any, for any value of y, I do not care what is the probability density function of x, that is what I am interested in now. So, if I just do this, that tells me the probability that x lies between x and x plus del x. So, that is the probability I am targeting. So, I can write this as limit del x tends to 0 that is the random variable. But remember, I also had y in the definition, but now I do not care about y. So, I am saying that y must be lying anywhere. So, from minus infinity to plus infinity. Okay. So, by definition I can write this, because I am only interested in x, that I want to restrict my x between x and x plus del x. So, that is my p x x into del x, okay, where del x tends to 0. But I have only the joint distribution. So, that also specifies y. So, y I do not want to keep any restriction. So, y can take any value from minus infinity to plus infinity. Okay. So, this is the probability I am targeting if I wish to only get x as marginal distribution, right. So, let us try to evaluate this thing. So, I can now write it to be limit del x tends to 0. Okay. So, now let us write it from the definition of PDF. So, y goes from minus infinity to plus infinity, therefore, the integration this p x y, this must be integrated over all y. Okay. So, that is the first task, minus infinity to plus infinity. For x, I should be integrating it from x to x plus del x, right. So, this integration should be x to x plus del x dx, right. X to x plus del x, yes, okay, that should be fine, is not it. So, I am integrating for y from minus infinity to plus infinity, and for x I am integrating from x to x plus del x. Of course, you can always argue that okay, it is excluding that value of x, but by the definition of integration I do not have to take that, okay. As long as I am integrating, if you just divide it into small area, the last one you can take it out, okay. So, this is what happens, right. So, this was according to the definition of probability theory. This is a probability, and we always know that any probability is given by the integration of its PDF from particular value that we have specified over here. So, for x, this is the value we have specified. So, that is where we are integrating, okay, and y, that is the value over which we are integrating. But we have to do another thing, because this is in the limit. So, maybe we can just define it as u and w. So, two dummy variable. We should not mix the limit with the internal integration variable, okay. That is all right. So, p x y u v, we are integrating from for y this and x this, okay. Now, the assumption is this del x tends to 0. So, within that interval, this is not changing, okay, as x varying, this is not changing. So, what I can do, I can actually separate out this integration. So, I can still write del x tends to 0, I can take x to x plus del x, this wherever that x variability is there, that means du, and y minus infinity plus infinity p x y u, suppose w dw, right. I can write it this way. Why I could separate this? Because I know that this particular thing is constant with respect to x. So, therefore, x integration and y integration can be separated out. I will have nothing within this, okay. So, this happens to be del x, because integrating du from x to del x plus del x. So, that should be del x. So, I can write limit del x tends to 0, this is del x, and this minus infinity to plus infinity p x y u w dw. Now, match these two, I get a definition of this, okay. So, immediately I can write my p x x is nothing but the integration with respect to the other variable, right. So, I take the same this one, same joint distribution, I integrate it with respect to y from minus infinity to plus infinity. So, that is called the marginalization. So, a particular, if it is a joint distribution, I want to marginalize it. So, I marginalize it with respect to the other variable, I get the marginal distribution with respect to whatever I am targeting. Okay. So, here we are targeting for x, then we have to marginalize it with respect to y. Same thing will be happening if we wish to target p y, then we have to marginalize with respect to x. Okay. So, that is how the joint distribution and marginal distribution are related. Now, let us try to see the conditional distribution, right. Okay. So, the Bayes theorem still prevails. I can always write the way we have written p x given y So, this is always true, we have already proven this. Okay. So, the joint distribution is related to the conditional distribution is somehow related to the joint distribution, or we should not talk about any distribution, we are just saying that probability the conditional probability is just related to the joint probability for a particular targeted value of x y. Okay. So, that is how we are discussing about these things. Now, what we can write, we can prove that this is also forming a PDF. What does that means? That means if I integrate it with respect to suppose x over minus infinity plus infinity, I must be getting 1, okay, because it is a finally this is nothing but given random variable y equal to y, this is the probability of x equal to x. Okay. Of course, this is a density function, but if I just take it multiply with del x and limit del x tends to 0, we can say that x lies between x and x plus del x. Okay. I will be able to talk about that probability. So, if that is the case, if I integrate this function with respect to x, because x is the variable over here, y is the condition. So, that condition I am not bothered about. If I integrate it with respect to x, I must be getting 1 if this should be a PDF or probability density function. So, I should be proving that. Let us see minus infinity to plus infinity p x given y dx. So, that is what I want to evaluate. So, I can write this as from this formula p x y, I can write it this way, right, just coming from this formula. It is p x given y is nothing but p x y divided by p y, right. This is the integration over x. So, y has nothing to do with it, I can take that out. What is this? This is just what we have proven now, that is the marginal distribution. Okay. I am marginalizing with respect to x, therefore, I will be left with y. So, that must be p y y divided by p y y, that is equal to 1. So, you could see that this is actually a PDF, okay, whatever we get, because we have just from the Bayes theorem directly correlated it, but now we could see that this is actually a joint PDF, conditional PDF, right. So, we can evaluate this PDF. Similarly, for other things also, like y given x, similar things will be getting. Okay. Now, from here conditional, we for the discrete random variable, we came to the independency, right. So, same thing we will do over here, p x given y, x will be independent of y if this is just this, it does not depend on y. So, whatever the value of y given y, I do not care, I will still get p x x. If this is happening, then I know that it is a independent event, means x does not depend on the occurrence of y. Y can happen, might not happen, still my x will be following the same thing. It is like that tossing the coin twice, does if it is a fairly uncorrelated unbiased coin, then what will happen? The second toss, the outcome does not depend on first toss what has happened, whether that was head or tail, I do not care, I will still have similar probability value of the second toss. Okay. So, that is same thing, independent. And if that is the case, now go to this Pxy definition. What it was? According to Bayes' theorem, this was Px given y Pyy. So, this was the definition. Now, this is according to this, right. So, we immediately see if they are independent, then the PDF also gets multiplied or separated out in the multiplication form. That is a very interesting theorem of probability theory. Okay. So, if two random events are independent, then I can always write this. Okay. Otherwise not, because otherwise you will not be able to write this thing. Okay. And immediately we can also get into this. This is actually the CDF of the joint distribution. So, this I can write as from minus infinity to x and from minus infinity to y, Pxy u, two dummy variable I have taken, du dw, right. So, I can write this. Now, the good part is, as they are independent, they can be separated out. So, I can write this sorry, it should be so, because they are separated, I can now separate these two integration. The integration with respect to variable u and w can be separated. So, I get minus infinity plus infinity Px u du integration minus infinity to x and minus infinity to y Py w dw, which is nothing but the fx x and fx y. So, this will be, I can, if I write, this must be equal to fx x and fy y, even their CDF gets multiplication form. Okay. So far these are the things which we could, means it is almost the similar thing that we have derived for discrete random variable, we have derived all those things for a continuous time random variable. Okay. So, in the next one, what we will try to see is what is the statistical property or measurement property that we can extract and how we relate them to probability. Okay. So, that is something we will try to see in the next class. Okay. Thank you.